So let's start the session. So I am Marchal, so I am the session chair of this session entitled Multimodal and Haptics. So we have 4 very great presentations in this session, and we will start with the first one. So the first one is entitled An Exploratory Expert Study for Multi-Type Haptic Feedback for Automotive Virtual Reality Tasks, and Alexander Achberger will be the presenter.
Thank you. So, hello, I'm from the University of Stuttgart, and today I'm presenting my paper. So, I came from the automotive industry, and there we use currently already virtual reality for different tasks. So one task, for example, is we can imagine they try to find out if a car can be assembled. So, like in this picture, they look if they, for example, a screw can be screwed. So for this task, they have 3 interaction types. So first, they have to grab a screwdriver and a screw. Then, after that, they feel the weight of the screw and the screwdriver, and then they have to position the screw and the screwdriver and maybe feel some collision with the virtual car. And this looks pretty simple, this use case, but there's a lot of problems right now in virtual reality. And these problems I found out in the automotive industry. And the number 1 problem here is that the haptic feedback is missing. And currently, so there are a lot of haptic feedback devices available, or not, there are some available, but they're mostly focusing on only one feedback type. For example, mostly they're focusing on collision on the hand, or maybe some are just on grabbing, or some on weight, but they are mostly unitype. And this task is not very realistic if we only have one of this feedback type, for example, just grabbing, because collision is missing. And switching between different haptic feedback devices is not really feasible, and that's the current problem there. And so our research goal was to investigate the benefits and drawbacks of combining existing haptic feedback devices into a multi-type haptic feedback system. So we don't want to develop a new one, we want to combine depending on what feedback types they can simulate. So in our paper we were focusing on 3 haptic feedback types: the weight simulation, grabbing simulation, and the simulation of collision. So our main contributions are that we first conducted a requirement analysis with automotive VR experts about their automotive VR tasks. And with this knowledge, we developed a new multi-type haptic feedback system that combined existing haptic feedback devices that meet these requirements. And after that, we evaluated our multi-type haptic feedback system with 12 automotive VR experts. So the first step was the requirement analysis, and there we interviewed 12 VR experts and watched their use cases, what they do in virtual reality. And with this knowledge and the data we gathered, we collected 11 requirements that were based on grabbing simulation and weight simulation. And with these 11 requirements, we looked in the literature and found 60 devices, and we evaluated and investigated them based on our requirements. And with this list of requirements and devices, we chose the best fitting devices that were on the one hand combinable, but on the other hand also meet the requirements we defined. And our solution were these 3 devices. So that's the sense gloves, the strives for collision simulation, and for weight simulation screw. So in a more detail, so the grabbing device, the sense gloves are commercial haptic feedback devices. They are already available, and they stop the finger movement when a virtual object is grabbed. The Strive device is a string-based haptic feedback device that can simulate collisions. So it works like you attach the string to a body part where you want to feel haptic feedback, in our case the hand, and you attach or position the device somewhere in the surrounding, and then it stops the string extraction when you're colliding, so that you have really the feeling of colliding against a virtual object. And this device can cover a workspace up to 2 meters based on its string length. And the last one, STRU, the weight simulation device. It's also a string-based weight simulation device that is worn like a shoe. And it consists of a motor that pulls a string that is connected to a controller or to the user's hand, and that simulates the weight. So together, when we combine all of them, the haptic feedback system looks like this. So as you can see, we used 3 strives. They are positioned in a triangular shape, and they are all attached via the string to the sense gloves, to the grabbing feedback device. And the weight simulation device, STRU, is also attached at the bottom of the sense gloves. And how it looks like, you can see in this video, with all 3 combinations of them. But we were not only interested in the combination of all 3 haptic feedback devices. So we were also interested in just a combination of 2 of them. As you can see here, for example, this is just grabbing and weight simulation. So we did not evaluate just one haptic feedback device because there's already a simulation evaluation available. Here, for example, you can see here collision and grab. And for the case where we having the grabbing simulation, we used just a default controller. It was the HTC Vive controller for the grabbing simulation. So after that, we evaluated this haptic feedback system in an expert study, and our goal was to evaluate the advantages, disadvantages, and technical limitations of our multi-type haptic feedback system in the context of a real automotive use case, and also the combination of each of these haptic feedback devices. And the task you can see in this video, so it's a real automotive use case where they try to replace a broken car component and to repair it. So they have to grab different objects with different sizes and different shapes and position them. And for example, here you can also see they have a lot of collisions there to find out if it really fits into the desired location. So as conditions, so as I already told you, we had 4 of them. So we had the combination of grabbing and collision, grabbing and weight simulation, collision and weight simulation, and all 3 of them. And for measurements, we gathered qualitative and quantitative data, but our focus were mostly on the qualitative data. And we also asked about speculative questions about ignoring the technical limitations to find out if the feedback is more interesting, also interesting without technical limitations. As participants, we had 12 automotive VR experts of the company of Mercedes-Benz. So we found different core findings, but because of the time, I will only go in more detail in only 3 of them, but you can see my paper and read all of them. So one core finding was that the weight and collision feedback in combination yielded the best results across all haptic dimensions, as you can see here, for example, in realism, utility, and so on. One participant, for example, told us that the direction can be estimated and the weight force gives an impression of realistic holding while still allowing free movement in the hand. Another core finding was that the first one was influencing it because we found out that the grabbing device had issues when grabbing small objects. In our case, they had to grab some small screws, And here the main problem was that there was a mismatch between the virtual and the real finger pose. So in our case, to grab a small screw, they had to do some annoying and strange, not realistic hand poses, and that felt unrealistic. And one participant, for example, said, the more frequently grabbing was used, the more evident it became that it was not useful and that the weight was more important. Another core finding we find out is that it was important that the participants or the user can decide their own trade-off between the technical limitations and the benefits, because they can decide which combination of haptic feedback devices they want. Because currently, every haptic feedback device has their own benefits, but also their own technical limitations. And depending on what for use case they have, they can decide which combination is really useful for them. And also one participant said that the users can consider or have to consider the relationship between effort and benefits. In our context, effort means the setup complexity or setup time. And yeah, we think that our flexible system could also be used in other domains because we can change the combination of haptic feedback devices and define our, based on the use case we want to simulate. So as I told you, we have different other core findings, but you can read them in the paper. But we also find out some limitations. One limitation was the limited mobility because it was a string-based setup. And for example, here the rotation was not with 360 degrees, was not possible in the context. We just had a one-handed use cases, and our task was in a specific domain. But yes. So in conclusion, we find out that this multi-type haptic feedback is important, especially in the automotive industry where we used it and has a lot of potential. We find out that combining existing feedback devices have some potential and benefits compared to building a new one, because if we have a new haptic feedback device, we can just replace or update it and keep the system unchanged, the rest of the system. And yeah, we still have some technical limitations, particularly concerning the grabbing device. And yeah, keeping the system flexible by allowing custom setups help to overcome technical limitations based on the specific use case. So, and thank you very much for listening. So I am up for questions.
Thank you very much for this great presentation. We have time for one or two questions? Okay.
Hello. Hi. Myself, Abhijeet Mishra. I just wonder, you have talked about multi-haptic feedback system, right? Multi-haptic feedback system.
Multi-haptic, we called it multi-type. So it was hard to define, so I have a definition about the feedback types we want to simulate.
Yes. I think that's perfect. I just want to know the purpose which you have mentioned, the positive side of multi-haptic feedback system. That's great. But all those haptic scenarios which you have demonstrated, they have also been evolved with some other previous demonstrations in the past. So what's further things I'm not getting, I didn't get through this output of your presentation, that this is also something left which we should think and look towards it.
So I'm not 100% sure. So mean these kind of tasks were already done?
Yeah. Now I've seen that like weight, you have seen string-based, and the gloves.
The gloves.
Yeah, integration is I have seen maybe two or in separately other one, but collectively these output of findings are I have found some other works as well, but I didn't get what's a new through this paper you are adding and you are delivering.
Okay,
Can
so
you please help me to understand?
okay, yeah, sure. So what we found mostly was that there was no devices that can simulate a collision so that you cannot penetrate, for example, object or can go through objects, but also the grabbing system. So we haven't found anything that was useful in the use cases for us on devices, because just a glove with, for example, kinesthetic feedback device, there you cannot simulate any weight or just collisions. You just feel maybe some vibrations, but with our haptic feedback device, you have really hard collisions so that you cannot go through any shapes. So you can do this task with closed eyes, for example. So that's the huge difference with just gloves with, for example, vibrations, so that it feels more realistic, and also the weight simulation, because in our context, weight is really important. You have to imagine they have to assemble maybe something that is weighs over 10 pounds, and then they have problems assembling it because of the weight. But in VR without weight, it would be pretty simple. And then it's not only about the grabbing feedback, it's also about weight. And so we haven't found anything that can combines the three haptic feedback in one device.
Okay, so yeah, so I think we don't have time for any other questions, but you have the Discord channel when you can ask other questions to the author, and I guess you will be there also at the end of the session if you have any other question. So let's thank again the speaker.
Thank you.
And so I will present our second presentation for this session. So the title of this presentation will be MobiTangibles, enabling physical manipulation experiences of virtual precision handheld tools, miniature control in VR. And it will be presented by Abhijeet Mishra.
So can I start? Can I start? Okay. Hello. Hello. Hello, everyone. Good afternoon. Myself, Abhijeet Mishra, and I am presenting my work on MobiTangibles, basically, which is about enabling physical miniature manipulation experience in VR of handheld tools. So basically, we all know that VR is being heavily used for education and training purpose. But if we are going to use VR device controllers in order to understand the physical miniature manipulation aspects, if someone utilize VR controllers, they will face obviously challenge, because VR controllers are generally involve button pressing experiences. So what kind of experiences I am talking about in this work, which are this, as highlighted through red marker. Obviously, in the past, previous work exists. Some, for example, like Voxel Hap. And about Voxel Hap is that they have a bunch of modules which are connected together. If you can, and there is one module which can be manipulated in a way as required in VR. Another work is Hap linkage, which allow users to manipulate, to design manipulations. But all these works have some certain limitations. The limitations are is a significant electronics part. Now think from the perspective of early researcher. All these works include some design using complex software-based prototyping. And so since above two are required, so hence it is also involved prior technical expertise. So in order to fill this gap, I proposed this MobiTangible work, which allow handheld tools miniature control manipulations in VR. It works based on phenomena of detecting magnetic field intensity. So whenever the magnet moves near to the sensor, which is commonly found in smartphone. the working principle which I leverage in order to enable the experience of physical manipulation miniature type in VR is this here. So let's understand. So for example, we have a smartphone. This is a smartphone boundary. And in magnetic field is that if the magnet is moved along the straight line and you want to measure magnetic field at a certain point in space, like for example P, and magnet is moving only along the straight line, then the relation between the intensity of magnetic field which is measured at point P will be in a proportional in an inversely way to the distance only through this relation. Obviously there is a B factor, B is earth magnetic field which comes into play, but in comparison to the intensity of magnet, the variation in earth magnetic field is very minimal, like it ranges between 22 microtesla to 67 microtesla. So as can be seen, the relation between BT and R is inversely proportional. Now I leverage this understanding in order to design manipulation, but to design manipulation, before I need to understand what kind of manipulation has to be designed. So to understand that part, I went through a lot of tools. I analyzed them, what kind of kinetic characteristics are embedded in them. And you can see some of the examples which are here. For example, vernier caliper having miniature manipulation of translation type, and injection is having a translation type miniature manipulation. Similarly, on the rotary side, we have a power Dremel and rotary and micrometer and so on. So in terms of after segregating tools, I found that two types of miniature manipulation commonly found in tools, like one is a translation and the one is a rotary. Based on this understanding, I enabled utilizing the same principle, that is working principle, and enabled experience of translation and rotary type both. So as can be seen, let's understand through this figure. So this is the boundary, a mobile case boundary, and there is a magnet which is attached, see here please, which is attached to this plate, which is a plastic plate. And whenever a user required, for example, he or she want to get educated on the translation aspect of translation type of miniature control, so that MobiTangible can be utilized in the VR. So this is the real part, digital and real case, how it look like, and it is also detachable, attachable. Obviously, slider is always there, and on the top there is a holder through which this rack and pinion type mechanism can be attached. And the advantage of rack and pinion mechanism is that it allows to give a feel of a rotary type, while inherently it will involve translation type manipulation, but a user will get rotary type feel while manipulation. So based on this understanding, now I then conducted a technical evaluation. So the purpose of this technical evaluation was that I need to evaluate what if this design which I fabricated, how it follows the working principle basically, which states that as the distance increases, magnetic field increases and vice versa. So to evaluate this and under varying conditions, this was the setup I utilized, phone, and this was the app which is freely available online to record a magnetometer sensor data. The procedure which I adopted is that I utilized a slider manipulator, because through which it is easy to shift the manipulations at a variable distance very easily. The distance are as like this. This is C0, C1, C2 and C6 up to. And I then perform the experiment in two scenarios. One is a less than 5 centimeter and the one is 250 centimeter, greater than 250 centimeter. Because EM devices are mostly a reliable factor which can affect the magnetometer sensor values. That's why I conducted using around EM devices. And this is the result as can be seen. So as the distance was decreasing, basically magnet is moving towards the point, which is sensor point. So magnetic field effect on that point was increasing. It was near to the electromagnetic device, and the same effect was obtained. Similar effect was also obtained from the away scenario also. But the question is that how are the values similar within a certain range for each points? So to test it, I conducted statistical analysis that confirmed that values are similar for each point using Wilcoxon signed rank test. So based on this understanding, I then calculated the inverse basically. Because since I want to map this understanding in VR, so utilizing the data of the previous results, I formulated this equation, which is here. That relation stated given the input magnetic field value, what would be the position of the manipulation. That understanding I evaluated and put it into the VR code. It's a basic equation without using any advanced algorithm. Then I conducted user evaluation where the purpose was to understand realism factor of miniature manipulation of handheld tools. To conduct this test, I recruited 15 participants and I evaluated my device in comparison to other two standard conditions, which is VR controls and bare hands, right? And participant was asked to interact with these tools, 3 from the translation type, 3 from the rotary type in VR in all the 3 conditions. Obviously, not only interaction one, we have also given a task which was associated to each of the tools, and the tasks were as follows. For example, it is a one-to-one mapping. In the figure this and previous figure are one-to-one map. So for example, in previous figure, the first tool is vernier caliper, and the first task was associated. User have to manipulate the vernier caliper jaws according to the thickness of the sheets in VR, so that their work can be made interactive while conducting the study. So accordingly, participants interacting with each tool in each condition and perform these tasks. So then 2 questions were asked on a 7-point Likert scale after completing each manipulation in each condition. One was related to realistic manner, another was related to fatigue aspect. These are 2 important aspects. While there are many, I evaluated only 2, these 2 only. And these were the interaction scenarios for each of the conditions, how user were interacting, whether it's a translation or the rotary. And this is the result. As can be seen, the MobiTangibles experience was very much high in comparison to providing realism and less fatigue aspects as compared to other 2 conditions. And it is also confirmed by the non-parametric fragment test followed by Wilcoxon signed test. Obviously, this work has limitation. Because it involves magnet, it can't be utilized. This case can't be utilized near to the objects which are sensitive to magnetic field. Currently, both manipulations can be used simultaneously, but currently it is not also required, since the tools which I am focused, they typically involve one type of manipulations only. And third is it cannot replicate shapes. So we have to think about shapes part, how it can be enabled in VR in a very simple, without adding a lot of logistics in terms of electronics and much advanced programming and so on, so that it can be enabled for those users as well who are in a resource constant settings. So for example, if I have to in this work, if I have to compare my work with some other toolkit like Voxel Hap, or which I have previously mentioned as existing work, I was not able to do. It's because I'm not able to fabricate those things in a very simple way in my settings. Hence, in order to enable your work to be evaluated very easily with by others, so we also need to think how to make it very lightweight and simple to use by each and everyone, on a global scale. Thank you.
Thank you for this presentation. So we have time for one small question. So maybe I have one question. So like your device appears to be quite big in the hand. So I guess depending on the size of the hand of each participant, it could have an impact on their feeling of the device. How did you manage to measure the size of the hand of the participants and to see if it has an effect on on the device and the perception?
Yeah, actually that part I have not evaluated, but since mobile can be held in a variety of manner, hence I utilize the mobile expert because in typical user situation of mobile, we can hold it like, for example, camera photography. We take the phone like this. So if user is manipulating the vernier caliper in VR, so that person knows that it is to be held like this. So the form factor is not coming because is not coming to the picture. I have not found that aspect as a feedback from the participants. But shape aspect I have already added because a lot of participants have provided that they are not able to explain the shape part. That is a common, most important limitation of my work. But this size aspect can be easily reduced and we can make it very lightweight also. Obviously it is lightweight, it is around 40 gram only, like a cover, which normal cover we have typically use. But it can be further reduced since it is a prototype.
Okay, thank you. Is there any other question? Like a small one? No? So still the Discord channel is open if you'd like to have additional question afterwards. So thanks again to the participants. And then we will continue this session about haptics and multimodal with our third presentation. So our third presentation is entitled Multimodal Feedback Methods for Advancing the Accessibility of Immersive Virtual Reality for People with Balance Impairment due to Multiple Sclerosis. And the paper will be presented by Rasel Mahmud.
Yes. All right. Hello, everyone. I'm Rasel Mahmud, an assistant professor of computer science from Kennesaw State University. And my co-authors are Alberto Cordova and John Quarles from University of Texas, San Antonio. I'm very happy to share our research paper, Multimodal Feedback Methods for Advancing the Accessibility of Immersive Virtual Reality for People with Balance Impairments due to Multiple Sclerosis. That's a long title, sorry. And let's start with some introduction. The popularity of virtual reality techniques is increasing day by day in many sectors. However, VR causes imbalance to healthy users, which is severe for people with balance impairments. Because people with balance impairment usually have some imbalance issue, and added imbalance by VR make it very difficult for them to get benefit from consumer VR applications. To solve the problem, we implemented and evaluated the effects of different feedback modalities on balance in VR. The objective of our research is to make immersive VR more accessible. For motivation, we found many prior research has come from the imbalance issues in VR, but minimal research has been conducted to reduce this effect. Also, most previous research only included participants without disabilities. We included both participants with and without disabilities in our study. Most rehabilitative approaches to improve balance in VR, have not used head-mounted display or only constrained to seated tasks. So we evaluated head-mounted display and evaluated standing tasks as well. Also, we found spatial, center of pressure, rhythmic, static rest frame, audio, vibration, or visual feedback are effective, at least in some extent, in non-VR environment, which motivated us to investigate this in VR. First, I'll talk about auditory feedback implementation and evaluation. We had two talks in our user study. First one is the standing visual exploration talks, and where we place different markers, left, right, top, bottom, front, in respective directions in the lab. We wanted to observe participants in the lab in a controlled fashion. And this was the standing reach and grab talks, where participants reached and grabs real and virtual objects. We instructed them to reach the objects, lift them through their chest level, and put them back in the same place with the controllers. For apparatus, we used HTC Vive Pro I, Vive controllers, balance board to collect balance data, and harness to protect them from falling. And we had 5 VR conditions. Among them, spatial auditory feedback outperformed others. For spatial audio, we played specialized white noise from Unity 3D using Google Resonance Audio SDK. When participants turned their head to left, right, front, or back, the audio volume increased. To to give them some sense, okay, it's changing. And we had several metrics for the study. COP velocity was the primary metric, and balance increased with the center of pressure when it's increased, and vice versa. We also had ABC and simulator sickness questionnaire, which is a 16-item questionnaire where participants rate their physiological discomfort. For statistical analysis, we use Sapir-Wheel test, QQ plot to test the data normal. Also, we use 2x6 mixed model ANOVA and two-tail t-test to measure the specific difference between any two conditions. For the study procedure, participants read and signed a consent form and filled different questionnaire at first. Then participants stood on a balance board while they are supported by a harness to protect them from falling. Then we measured their balance for the standing visual exploration tasks and standing reach and grasp tasks with 3 trials for each task. VR tasks are all the replication of the baseline tasks, except they are performed in VR with different kind of feedback. Finally, participants filled out SSQ and demographic questionnaire, and we paid them $30 per hour. For the result, spatial audio outperformed other conditions for both tasks, standing visual exploration and standing reach and grabs for both groups of participants. Now, I'll talk about the biotactile feedback implementation and evaluation. The figure shows the participant performing the standing visual exploration tasks in real and virtual world. The study procedure was same as the auditory feedback, except we provided them biotactile feedback instead of auditory. And for apparatus, the tactile for arm provided biotactile feedback to the arms. The forehead tactile was attached to head-mounted display to provide biotactile feedback. Haptic taxoid was used to provide biotactile feedback in the body. The figure shows the biotactile motor positions. We used total 52 biotactile motors. Those are very small motors, and for arms, forehead, and front side and back side of the vest. For study condition, again, we had 5 different conditions, but we found spatial biotactile outperform other conditions, where we used the same specialized white noise for the auditory feedback, and we converted that to biotactile feedback. And for this condition, the forehead device vibrated at varying levels when user tilted their head to left, right, front, or back. The base vibration was modified depending on the position of the participants. We tracked that from a vibe tracker. The vibration of the arm sleeves was altered based on the controller positions while they are doing the virtual tasks. And we again found spatial biotactile outperform other conditions for both tasks, standing visual exploration and standing reach and grab tasks. Now, I'll talk about the visual feedback techniques, implementation and evaluation. We used a simple plus sign surrounded by 4 L-shaped boundaries for visual feedback. The frame was suitable because participants with multiple sclerosis has less physical functioning, and they are prone to cyber sickness with a lot of visual signals. That's why we choose a very simple sign to show them some visual feedback. And for study condition, again, we chose 5 VR conditions based on the literature. Those work better for non-VR environment. And we found for static visual conditions, it outperformed other conditions where the frame was affixed to the user's view. That means the frame was moving when the participant was moving their head in the VR environments. As I said, static visual feedback outperformed all other conditions, but the only difference this time, this was only working for participants with balance impairment, not for other groups. And finally, from those results, we thought we'll investigate the multimodal feedback techniques implementations and evaluate that. The first research question was, does multimodal feedback, which is the combination of auditory, biotactile, and visual feedback, work better than a single feedback modality? And if yes, which combination works best? And we also wanted to see if the mental load, presence, and fatigue level are increasing or decreasing based on the feedback modality. We recruited 72 participants, 36 with balance impairments due to multiple sclerosis, and 36 without balance impairments. And for the multimodal feedback study, the real environment, virtual environment, real and virtual tasks, and the system setup was same as the previous study. We also use same research design and procedure for previous studies. For the questionnaires, we used previous demographic SSQ and ABC questionnaire, but we added the mental load, fatigue level, and presence and system usability questions for this study to see how those things are changing. For the feedback intensity, we set it based on users' comfort level, so we allowed them to set it. And we had 9 different study conditions for the study. For the auditory, vibratactile, and visual feedback condition, we selected spatial auditory, spatial vibratactile, and static visual feedback as those outperform other conditions in our previous study. Then we investigated the combination of different feedback modalities. For example, auditory plus vibratactile, auditory plus visual, vibratactile plus visual, and finally, multimodal, which is the combination of auditory, vibratactile, and visual feedback. And we collected balanced data and data from 6 sets of questionnaires. We used some statistical analysis. However, this time we used 2x9 mixed model ANOVA instead of 2x6 because we had 9 different conditions this time. And we found for both groups of participants, the multimodal feedback condition outperformed all other feedback conditions significantly. The study conditions with 2 different modalities performed significantly better than the study condition with only 1 feedback modality. For single feedback modality, we also found auditory feedback outperform vibratactile and vibratactile feedback outperform visual feedback significantly. We found similar result for standing reach and grab stacks, where multimodal feedback outperform other conditions significantly. While we compared the multimodal feedback condition with the single auditory, vibratactile, or visual feedback, we found the mental load and fatigue level were significantly higher in the multimodal feedback condition. From the single system usability question, we also found all participants rated fully agree that the study conditions are usable. So from key findings from our study, first, we found balance in VR, imbalance issues caused in VR with no additional feedback. And second, any additional feedback of auditory, vibratactile, or visual improve balance in VR. Third, auditory feedback outperform vibratactile feedback, and vibratactile feedback outperform visual feedback significantly in our study. And fourth, any combination of feedback modality perform better than a single modality, and multimodal feedback outperform all other conditions significantly. However, with the addition of sensory feedback, mental load and fatigue level increased. Presence changed a little bit, but it was not a significant change. This research will help researchers better understand the various kinds of auditory, vibratactile, visual, and multimodal feedback modalities for maintaining balance in immersive virtual environments. This will also help to create more usable and accessible immersive experience. In our future work, we want to develop an adaptive and personalized multimodal feedback system to increase the accessibility and safety of immersive VR. We'd also like to develop a system so that we don't need to use the balance board and the user need to stand on the same place. Maybe we plan to make some pose estimation models so that users can move freely, still we can measure their balance and still our feedback modalities work. Here are the references, thank you.
Thank you for the presentation. So we have time for 1 or 2 questions.
Well, Jainendra here from IIIT Delhi. Thanks, Mahmud, for the nice presentation and nice work, actually. So I was wondering, since you already looked at the individuals with the balance disorders, so in this case, were you able to benchmark their balance, attitude or balanced approach before even starting anything? So for example, different individuals, they may have different types of balance disorders, and even individuals, those who do not have any clinically diagnosed balance disorders, their, let's say, the ability to balance also differs. So were you able to, benchmark their ability to balance before, starting any experiments? And also, did you see any difference with respect to that?
Okay, thank you. That's a good question, actually. So before, that was our participant recruiting part. Before we recruit participants for our study, we have an interview with phone call, and we have set some questions. We asked them You shouldn't have any medication for like your balance changing, like improving or whatever issues you have. You should be a normal person without no medication, and you should have a balance level. We have a rate for MSSQ, we have a scale. So normally we say, okay, you should be within this scale, and if you are not within this scale, then we won't hire you for our study. So that we try to make it very static, how do I say that? So make it simple for all participants, simple and fixed actually. So that it doesn't vary too much from one participant to another. Someone has maybe imbalance level of 10 and someone has 1. Now, if I recruit them in the study, that is problematic. Now, it will hard for me to understand. So we didn't investigate like different level, like say, imbalance level 1, 5, 10. We didn't group that way because we had shortest with participants, and it was hard to recruit participants with especially multiple sclerosis. So we only hired people who has balance impairments and just only one level, like 4 to 5. So then we had a imagination like they are on the same level, and we'll get the data almost close for all participants, not like varying from their balance impairments. So same level of balance impairments we tried to recruit.
One follow-up question or no?
Yeah, sure.
Oh, yeah.
So, just a quick question. Great presentation, thank you so much. How do you prevent, I'm just wondering, how do you prevent misinterpretation of feedback? Because there's a chance that the feedback that you provide through these different modalities would be misinterpreted by the person who's losing their balance, right?
So,
or if you could
I'll
elaborate on
provide
the nature
you
of,
meant I'll provide the feedback, but still the participant is not sure, like this is the feedback for heart or something.
or how they understand, how they perceive and interpret the feedback may actually differ from one individual to another.
Okay.
Right,
Yeah.
and if you could, for example, give us some example on the nature of this feedback, different modalities of feedback. That would be
Okay, yeah, I think that's a good question. So before we start the user study, we normally tell them the study procedure and how the feedback will work. So they have some initial idea, okay, this kind of feedback I'm going to have while I'm navigating in the virtual world. So for example, for the spatial auditory feedback, when participant moved from tilted their head to like left, right, front, or back, for example, when the participant is moving the head from left side, we increase the audio volume in the left ear, the head-mounted display, the left earphone. And we told them before, like when you are saying like you are hearing increased volume auditory feedback in your left ear, that means you are tilting your body or your head to the left side. So you should correct your posture. And for vibrotactile feedback, like similar way, when participant was tilting to the left side, only the left side of the vest was vibrating, and give them some feedback, hey, you are swaying this way, so you should correct your posture to the center position so that you don't fall. So, and for the visual feedback, like we had a plus sign, when the participant was tilting to left, the plus sign also was tilting to left, so that he or she can get some sense, oh, I'm going this way, so I should correct my posture to keep my balance better. Did you get it a little bit? Okay. Yeah, then. Yes.
Okay, so thank you. Let's thank again the presenter.
Thank you so much.
And it's now time for our last presentation of the session. The presentation is entitled Detectability of ETHD Position and Speed Redirection for VR Haptic, and it will be presented by Yuqi.
is 600?
No, it's not plugged. Again? I will just unplug and plug.
Yeah. Yeah, it detects the.
Yeah, well, you're not going to see it here. I'm not seeing it at all.
Okay. Okay, thank you. Hello everyone, my name is Yuqi Zhou. I'm from Purdue University, and today I'm going to present our work on redirection for ETHD. Okay, so imagine that the user swinging, should be right, swinging the virtual stick to hit the virtual object. When the stick makes contact, the virtual object needs to respond convincingly and probably stop the movement of the virtual stick and give the user the adequate haptic feedback to feel real. Sure, you can place a physical object at the exact location as the virtual object, align them perfectly, and in this way, when the user interacts, when they actually hit the target, they feel a stop from the physical object, and they can sense and see their virtual and physical interaction at the same time. And it's a perfect happy feedback. But the problem is you cannot place a physical object at the position of every virtual object, right? So it's just limiting the usability of dynamic virtual environments. So one solution is to have a robot move the physical object. And such a device is also called encounter-type haptic device. Here is an example of such a robot with a reach range of 50 by 50 by 30 centimeters. However, the robot's reach is still limited, right? And expanding it further requires more cost and space requirement. So we ask ourselves, can we create the illusion of a larger reach using some visual tricks? And the answer is, of course, we can. And one example is called redirection. So what exactly is redirection? For a convincing happy feedback, usually it requires synchronizing the virtual and haptic objects. And this in turn requires a perfect alignment between the physical and virtual objects. Or does it really have to be? Right. Interestingly, if the user sees the interaction and feels the adequate haptic feedback at the same time, and the misalignment between the physical and virtual objects are minimal, then the user cannot tell that there is this discrepancy between the virtual and physical objects. So the question is, how far can we push this reach of ETHD with the help of redirection? For stationary objects, we can just simply apply the detection thresholds we established in previous studies. For example, in our previous paper, we measured the detection thresholds using the same stick length under similar setup, and the detection thresholds were 15 centimeters. But since we have a moving robot, we can apply redirection to moving objects. And the question is, can we still use the same thresholds for those redirections? And we need to find out. So in this paper, we investigate how the moving virtual object affect the detection thresholds of redirection. Well, we consider two factors. First is the presence of the moving virtual object itself. So if the user gets distracted by the moving virtual objects, we can have larger detection thresholds. But conversely, if they get more focused on the moving virtual objects, the detection thresholds can be smaller. Another factor is the speed difference between the virtual and physical objects. So the ETHD's range can be extended on all four directions: up, down, left, or right. And if you consider depth, that will be more. So when objects are moving from one point to another, the speed difference between the virtual and objects may be easy to detect. So if the user is very good at detecting the speed difference between the virtual and physical objects, then the effectiveness of the redirection is compromised, making it harder to apply the detection thresholds. To explore these two factors, we conducted a user study with 2 experiments. So in the first experiment, we assessed the detectability of redirection for both stationary and moving virtual objects. We used the yes no design to ask if they noticed any irregularity in the hand or stick movements. We tested 2 moving directions, and so it's horizontal and vertical, and 2 relative positions between the virtual and physical objects. So whether the virtual object is following or preceding the physical object. Here are the results of the detection thresholds. We tested redirection at various discrepancy levels and fitted sigmoid measure function out of those points. The negative threshold values means that the virtual object is ahead of the physical object, and the positive values are the opposite. A speed of 0 centimeters per second means that the objects are stationary. And as you can see here, the results are pretty symmetric for different relative positions, right? It's very, very, very close when it comes to absolute values. So it turns out like the relative position doesn't really have a huge impact. And it's worth pointing out the detection thresholds for moving virtual objects are not significantly smaller than those for the stationary ones. So sometimes it may become smaller, like slightly smaller than those for the stationary ones, but they're not significantly different, meaning the position, meaning the motion itself doesn't have a huge impact on the detectability of redirection. In the second user study, we measured the detection thresholds for speed difference between the virtual and physical objects. We also tested 2 moving directions and the relative speeds, so whether the physical object is faster or slower than the virtual object. We also used a yes-no design in this case. Here's the results of the second experiment. The negative values corresponds to the virtual object moving slower than the physical object. And the positive value indicated the opposite. When moving slower, the virtual object can reach speed as low as 3 centimeters per second. So here is the speed of the physical object, and the speed of the virtual object can be as low as like 2.7 centimeters per second. And in contrast, when moving faster, the virtual object can exceed the speed of the physical object by up to 15 centimeters per second. And it was very surprising to us how bad the users were when detecting the speed redirection. Because as you can see here, for the data points to fit the sigmoid curve, the correct detection rate was significantly lower than 100%. It's close to 50%, meaning the user can hardly detect the difference, the speed difference between the virtual and physical objects. Okay, combining the results from the first and second experiment, we illustrate the relationship between the ETHD speed, reach, and the maximum time for the object in motion. So basically, this is the maximum time the user can put their stick on the objects while they're moving. This graph is based on the detection thresholds from both experiments. In the red region of the graph, haptic feedback is constrained by the user's sensitivity to redirection. For example, at point B, without redirection, the ETHD can move for up to 2.5 seconds with a 75 centimeters reach and 30 centimeters per second speed. But with redirection, the overall duration of the virtual object drops to 2.42 seconds. So this shorter duration of the virtual object suggests that the ETHD could have utilized more redirection to extend its reach for the reach range. So basically, this number here, the extended reach range can be larger than the thresholds. On the other hand, in the green region, the haptic feedback is constrained by the mechanical limitations of the ETHD. So for example, at point A here, the physical object can move for up to 1.5 seconds with a 45 centimeters reach and 30 centimeters per second maximum speed. But with redirection, the virtual object can move for 1.76 seconds, which is longer than the physical object, meaning we cannot fully leverage redirection to extend the reachability of the ETHD. To maximize the redirection, the detection thresholds we measured, we'll need an ETHD with larger physical reach or a slower speed. On the decision boundary here, the ETHD can fully utilize the benefits of the redirection without any compromise. So for example, at point C here, both physical and virtual objects can move in sync for up to 2.27 seconds. And of course, the detection thresholds we measured, the 70 centimeters from the first experiment and 15 centimeters per second from the second experiment are not absolute. They can vary depending on the different scenarios and conditions, like stick length or different use cases, different applications. Great, that's all for today, and I'm ready for your questions.
Thank you for the presentation. So we have time for questions.
Hi, I'm Tong Yu from University of Minnesota. In traditional redirected walking literature, we have observed a huge individual difference in the measured detection threshold. But I would expect, like in your study, the individual difference will be smaller, but I just wanted to double check with you if how big is the individual difference of the detection threshold you measure, and is that comparable to traditional redirected walking detection threshold, or is it larger or smaller? Thank you.
Yeah, that's a good question. So it requires to fit the sigmoid functions on individual values. I would say from we didn't actually calculate the individual thresholds for this experiment, but from what we have found in the past, the individual difference is pretty small.
Good.
Yeah. So also from like the interviews, the communications with the participants, they always respond like with similar like findings. For example, when the difference is large enough for them to detect, they always say, like during the study, they always say, hey, I found this very like very obvious. Like I can sense like my stake is going away or something like that. So I'll say the individual difference is quite small.
Thank you so much. That's a very nice presentation.
So maybe a small question from my side. In addition to the previous question, so did you observe any difference when you go from left to right or right to left, depending on your dominant hand? I was not sure,
but dominant hand? Yeah. Oh, so all the participants we had are right hand. So we
okay,
didn't have
and did you observe something different, like when they were going from left to right or right to left?
So we have the data here, and so for the first experiment, this it's not about from left to right and right to left, but I think that's a good question, to be honest, to further investigate. We didn't add the moving direction because it was kind of redundant, and it just doubles the amount of tasks we had to do. And when we are doing the pilot study, it didn't make a huge difference by then. So, but I think that's a question we need to investigate in the future. Thank you.
Okay. Any question? No? So let's thank again the presenter and all the presenters of the session. And as a reminder, so you have the Discord channel when you can ask a further question if you'd like for the presenter, and they are there now if you'd like to ask question in person. So thank you again for attending the session.